Linear Algebra II, Lecture 6, Change of Bases. Let us start with a quick recap of a matrix of a linear operator. Let V and W be two linear spaces. Recall that a map F from V to W is called linear provided that it preserves the addition and multiplication with scalars. In the following sense, that the f of x plus y is equal to f of x plus f of y, and f of lambda x is equal to lambda f of x for all x, y, and lambda. Now let us choose a basis in V, denoted bold V, which consists of the vectors v1 and so on, vk. So note that this means that the dimension of V is k. Let us also choose a basis in W, denoted bold W, and consisting of the vectors w1 and so on, wm. So in particular, the dimension of W is m. Then the matrix of F with respect to this choice of bases, V and W, is defined as follows. The first column of this matrix consists of the coordinates of the vector f of v1 in the basis W. The second column of the matrix consists of the coordinates of the vector f of v2 in the basis W, and so on. The main property of this matrix is the following one. For any element x in V, if we want to compute the coordinates of the element f of x, so this is now an element in W, with respect to the basis bold W in W, then in order to determine these coordinates, we need to take the matrix of our linear operator f in the bases W and V and multiply this matrix on the right with the vector of the coordinates of our element x of V in the basis bold V. And the question which we want to answer today is what happens if we choose a different basis in V and a different basis in W. So what kind of data records a new choice? So let bold V tilde be another basis in V. It might coincide with bold V or it might be different. So assume that it consists of the vectors v1 tilde and so on, vk tilde. Note that it also consists of k vectors because the dimension of V is k. So all bases in a finite dimensional vector space have the same cardinality. Then we have the transformation matrix T from the basis V to the basis V tilde, which is defined in the following way. The first column of this matrix consists of the coordinates of the vector v1 tilde in the basis bold V. The second column of this matrix consists of the coordinates of the vector v2 tilde in the basis bold V, and so on. So this is the set of data which defines a new basis relative to the original basis bold V. Similarly, let W tilde, the bold W tilde, be a new basis in W consisting of the vectors W1 tilde and so on, Wm tilde. Again, this basis has m vectors because the dimension of W is m. Then we have the corresponding transformation matrix from the basis bold W to the basis bold W tilde, and the columns of this matrix are exactly the coordinates of the new basis elements with respect to the old basis. Okay, so now we can formulate the main result of this lecture, the change of basis formula. Recall that we have a connection between the transformation matrix from one basis to another basis and the transformation matrix back. The transformation matrix from the basis W tilde to the basis W is equal to the inverse of the transformation matrix from the basis W to the basis W tilde. So the base change formula now reads as follows. The matrix of the linear map F with respect to the new basis W bold tilde and both v tilde is equal to the following product. So from the left, we start with S inverse. So this is the inverse of the transformation matrix from bolt W to bolt W tilde. Then we have the matrix of F with respect to the old basis, the matrix of F for bolt W and bolt V. And the third factor is the transformation matrix T from the basis V to the basis V tilde. So if we put all the bases in this formula, we will get that the matrix of F from W tilde to V tilde is equal to the inverse of the transformation matrix S from W to W tilde times the matrix of S in W and V, and then times the transformation matrix from V to V tilde. Or we can change the inverse of the transformation matrix from W to W tilde to the transformation matrix from W tilde to W. Proof. To prove this, let us take arbitrary x in V. We know that the coordinates of f of x in bolt W are equal to the product of the matrix of f with respect to V and W times the coordinates of x in V. We also know that the coordinates of x in V are equal to t times the coordinates of x in V tilde. And we also know that the coordinates of f of x in W are equal to s times the coordinates of f of x in W tilde. So we can now plug in the expressions for the coordinates of x in V here and the coordinates of f of x in W here. The outcome is as follows. S times the coordinates of f of x in W tilde are equal to the matrix of F with respect to V and W times T times the coordinates of X in the basis V tilde. So now we can multiply this with S inverse on the left, and we will get the following expressions that the coordinates of f of x in W tilde are equal to S inverse, the matrix of F in V and W, times t, and then times the coordinates of x in V tilde. So now we can compare this expression with the expression that the coordinates of f of x in W tilde are equal to the product of the matrix of f in the new basis times the coordinates of x in the new basis. So if we subtract one of these equalities from the other, the left-hand side disappears, it becomes 0, and on the right-hand side we can move out the coordinates of x with respect to V tilde to the right using distributivity, and we will get that 0 is equal to the difference between S inverse, the old matrix of F, times t, minus the new matrix of F, times the coordinates of x in V tilde. And this equality is true for any element x in V, in particular for any vector, which you can write here on the right-hand side. Since this is true for any vector, it follows that the factor on the left-hand side of the right-hand side of our equality is equal to 0. In other words, 0 is equal to S inverse old matrix of F t minus the new matrix of F. In other words, the new matrix of F is equal to S inverse the old matrix of F and t. So this completes the proof of the base change formula. Let us now talk about composition of linear maps. Let V, W, and U be three vector spaces. Let V from V to W be a linear map, and G from W to U be another linear map. Then we have the composition G composed with F, and this is a map from V to U. It is defined as follows. The value of the composition of G and F at the element V in V is equal to G applied to F of V. So now we make the observation that the composition of G and F is a linear map. In other words, the composition of two linear maps is a linear map. To prove this, we need to check the properties of the linear map. Let us start by computing the composition of G and F applied to x plus y. So by definition, this is equal to G applied to f of x plus y. But f is linear, so this is equal to G applied to f of x plus f of y. And since G is linear, this is equal to G of f of x plus G of f of y. So by definition, G of f of x is the value of the composition of G and f at x, and G of f of y is the value of the composition of G and f at y. And similarly, one shows that the composition of G and f applied to lambda x is equal to lambda applied to the composition of G and f applied to x. In other words, this shows that the composition of G and f is a linear map. Now let us discuss how one computes the matrix of the composition of two linear maps if one knows the matrices of each factor. For this, we choose a basis bold V. In V, it consists of V1, V2, and so on, Vk. We choose a basis bold W in W, consisting of W1 and so on, Wm. And we choose a basis bold U in U, consisting of U1, U2, and so on, Un. Theorem: the matrix of the composition of G and F with respect to the bases V and U is equal to the product of the matrix of G in the bases U and W times the matrix of F in the bases W and V. Proof: for any element x in V, we know the following things. So first of all, the coordinates of f of x in the basis bold W are equal to the product of the matrix of F with respect to the bases V and W times the coordinates of x with respect to V. Next, the coordinates of the vector G of f of x in the basis U, this vector of coordinates is equal to the product of the matrix of G in our bases W and U times the coordinates of f of x in the basis bold W. On the other hand, the coordinates of the same vector G of f of x in the basis U, by definition G of f of x is exactly the value of the composition of G and f at x, and this is equal to the matrix of the composition of G and f in the basis U and V times the coordinates of x at V. So consequently, if we compare these two equalities and plug in the first equality here, we will get that if we take the matrix of the composition of G and F in the basis V and U and multiply with the coordinates of x in the basis V, we will get the same thing, which we will get if we take the product of the matrices of G and F and multiply them with the coordinates of the vector x. And this is true for any vector x. Since this is true for any vector x, we can deduce that the matrix of the composition of G and F in our basis is equal to the product of the matrices of G and the matrix of F. So this completes the proof of our theorem. So now when we talked about the composition of linear maps, we can talk about invertible linear maps. Let's recall what an invertible map is. Let x and y be sets and F a map from x to y. The map F is called invertible provided that there is a map G from y to x such that the composition of F and G is equal to the identity map on y, and the composition of G and F is equal to the identity map on x. If such G exists, it is unique, and it is called the inverse of F and is usually denoted as follows: F to the power minus 1. Observation: let V and W be two vector spaces, and let F be a linear map from V to W. If the map F is invertible as a map, then the inverse of this map is also a linear map. To prove this, let's check one of the axioms for the linear map, and the remaining things will be an exercise. For a real number lambda and for element x in V, the fact that f is linear means that, in particular, the value of f at lambda times x is equal to the lambda times f of x. So this is now the equality in W, so we can apply our inverse f inverse to this equality. So what we will get here on the left-hand side, we will get f inverse applied to f of lambda dot x. So by definition, this is the composition of f inverse and f applied to lambda dot x. But because of the definition of the inverse map, if we take f inverse composed with f and apply to any vector z, by definition, we will get the identity map applied to z, and this is z. So on the left-hand side, we will get just lambda times x. And on the right-hand side, we will get f inverse applied to lambda times f of x. But the map f is surjective because it has an inverse, so it is surjective. So we can replace f of x. We can denote it by y and just replace the expression f of x by y, and y is in any element in W. And then, since f is injective, there is a unique element x in V, which is sent to y. In other words, x is equal to f inverse of y. And so we can now read this last equality as f inverse applied to lambda dot y, this is the right-hand side, is equal to lambda dot f inverse of y. And this is exactly one of the axioms which guarantees that f inverse is a linear map. The other properties necessary to ensure that f inverse is a linear map are checked similarly. So now let us talk about the matrix of the inverse of a linear map. Theorem: let f from V to W be a linear map. Then the map f is invertible if and only if the matrix of this map is invertible for some choice of bases in the first space and in the second space. And in fact, if it is invertible for some choice of bases, it is invertible for any choice of bases. So this is claim 1. Claim 2, if f is invertible, then the matrix of the inverse of f is equal to the inverse of the matrix of f. So if we choose the same basis. Proof: if f is invertible, then the composition of f and its inverse is equal to the identity on V, and in the other order, it's equal to the identity at W. And we know that the matrix of the identity map is the identity matrix. So if we just apply taking the matrix to these two equalities, we will get that the product of the matrix for the inverse times the matrix of f is equal to the identity matrix, and in the other direction, the product of the matrix of f times the matrix of inverse is equal to the identity matrix. So the sizes of these identity matrices correspond to the dimensions of the original spaces. And this is exactly the definition that the matrix of f is invertible and the matrix of f inverse is its inverse. So this proves a part of the first claim and completely the second claim of our theorem. So it remains to show that if the matrix of f is invertible, then f itself is invertible. So let us now assume that the matrix of f in our bases V and W is invertible, and let us prove that the linear operator f is invertible. Let A be the inverse to the matrix of f. Define the map G from W to V as follows. So if we take an element y in W, then the coordinates of G of y with respect to the basis V are by definition equal to the product of A and the coordinates of y in the basis W. So using the properties of the matrix multiplication, one immediately checks that this is a linear map and that A is the matrix of this linear map. If you look at this equality, it is just defined so that A is a matrix of G. And by construction, G is an inverse of F. So this shows that F is invertible. One nice corollary of this, if a linear map F from V to W is invertible, then the dimension of V is equal to the dimension of W. And the reason for this is that we know that an invertible matrix is quadratic, and we have just proved that F is invertible if and only if its matrix is invertible. So we need the matrix to be invertible, and we know that the number of rows in the matrix is the dimension of the target vector space, and the number of columns is the dimension of the original vector space. For a quadratic matrix, these two dimensions should coincide. Okay, let us now do some examples. Consider the following basis bold V in R3. So the vector v1 is 0, 0, 1, the vector v2 is 0, 1, 1, and the vector v3 is 1, 1, 1. It is not very difficult to check that this is indeed a basis in R3. Let F from R3 to R3 be a linear map whose matrix with respect to the basis V, so we have the same vector space as origin and target, and we have only one basis, so it's a matrix with respect to this basis. So the matrix of F in the basis bold V is 1, 2, 3, 2, 3, 1, 3, 1, 2. So we need to determine the matrix of F in the standard basis E. We need to determine the value of F at the vector 1, 2, 3. And we need to determine whether F is invertible or not. So the last task to determine whether F is invertible or not is the easiest one. We know that the linear operator is invertible if and only if its matrix is invertible. And the matrix is invertible if and only if its determinant is non-zero. So we can simply compute the determinant of F. So the determinant of this matrix is equal to 1 times 3 times 2 plus 2 times 1 times 3 plus 2 times 1 times 3 minus 3 times 3 times 3 minus 2 times 2 times 2 minus 1 times 1 times 1. And so we will get 6 plus 6 plus 6, this is 18, minus 27 minus 8 minus 1. This is minus 36. We will get minus 18, which is non-zero. And so the matrix of F is invertible, and consequently F is invertible. So now, in order to determine the matrix of F in the standard basis, we need to use the base change formula. In other words, we need to find the transformation matrix between the standard basis and the basis V. The easy one is a transformation matrix from the standard basis to V, because then we just need to write the vectors in our basis V as columns in this matrix. So the transformation matrix from E to V is the matrix which we read column-wise, 0, 0, 1, 0, 1, 1, 1, 1, 1. We want to use the base change formula, which says that the matrix of F in the standard basis is equal to the product of the transformation matrix from the standard basis to V times the matrix of F in the basis V times the transformation matrix from V to E. We know the first transformation matrix, we need to find the second one. But we of course know that the second one, it's a matrix in the opposite direction, so this is the inverse of the original transformation matrix. So let us compute this inverse. So we take our original transformation matrix from E to V, then we write the vertical line, and then we put the identity matrix to the right, and now we try to reduce all this to the row echelon form using Gauss elimination. So in order to make 1 here in position 1, 1, we swap the first and the third row. So now the first row is 1, 1, 1, 0, 0, 1. The second row is the same, 0, 1, 1, 0, 1, 0. And the last row is 0, 0, 1, 1, 0, 0. So the first column looks fine. We have 1 here and 0 everywhere else. In the second column, we have 1 in position to 2, so we need to kill 1 in position 1, 2. So we subtract row 2 from row 1. Rows 2 and 3 remain the same, and the new row 1 becomes 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1 is 0, 0 minus 0 is 0, 0 minus 1 is minus 1, 1 minus 0 is 1. So now we are done with the second column. In the third column we have 1 here, and we need to kill this one. So we subtract row 3 from row 2. Rows 1 and 3 remain the same, and the new row 2 becomes 0 minus 0 is 0, 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 1 is minus 1, 1 minus 0 is 1, and 0 minus 0 is 0. And now we have the identity matrix here, which means that our answer, the inverse to the original matrix T, is here on the right-hand side. So T inverse is the matrix 0, minus 1, 1, minus 1, 1, 0, 1, 0, 0. So now we can use the base change formula to compute that the matrix of our operator F in the standard basis E is equal to the product of the transformation matrix from E to V times the matrix of F with respect to V times the transformation matrix from V to E. So this is a product of the matrices 0, 0, 1, 0, 1, 1, 1, 1, 1 times, so this matrix was the transformation matrix from E to V. Next we have the matrix of F in V. So by the formulation this was 1, 2, 3, 2, 3, 1, 3, 1, 2. And then we have the transformation matrix from V to E. This is 0, minus 1, 1, minus 1, 1, 0, 1, 0, 0. So if we compute the product of these three matrices, we will get 1 minus 2, 3, minus 1 minus 1, 5, 0, 0, 6. So this is the matrix of the linear map F in the standard basis. And the final task, we need to find out the image of the vector 1, 2, 3 under F. So 1, 2, 3 is an element in R3, and all elements in R3 coincide with the coordinates of these elements in the standard basis. So we can take the matrix of F in the standard basis and multiply this matrix with our element 1, 2, 3. So what we will get, 1 minus 4 plus 9, this is 6, minus 1 minus 2 plus 15, this is 12, and then 0 plus 0 plus 18, which is 18. So f of 1 to 3 is equal to 6, 12, 18. Okay, let us now talk about the vector space which is formed by all linear maps. So let V and W be two linear spaces. Consider the set denoted by L from V to W, so L is just linear maps. So this is a set of all linear maps from V to W. For two linear maps F and G, define their sum F plus G as follows. So the value of F plus G at an element X is defined as F of X plus G of X. Observation: if F and G are linear maps from V to W, then their sum is also a linear map from V to W. Proof. Again, let us check one of the axioms of the linearity and others are similar. So applying F plus G to X plus Y, by definition this is equal to F of X plus Y plus G of X plus Y. Using the linearity of F and G, the first summoned is F of X plus F of Y, and the second summoned is G of X plus G of Y. Using the axiom of vector space, we can swap these summands. We get f of x plus g of x plus f of y plus g of y. But again, by definition, f of x plus g of x is exactly the value of f plus g at x, and f of y plus g of y is exactly the value of f plus g at y. And similarly, one can check that f plus g applied to lambda x is equal to lambda times f plus g applied to x. We can also define the scalar multiple of a linear map. Let lambda be a real number and f a linear map from V to W. So we define the new map lambda.f from V to W in the following way. So lambda.f applied to x is by definition lambda times f of x. And a similar observation, so if lambda is a real number and f a linear map from V to W, then lambda.f is a linear map from V to W. Proof. Again, let us check one of the axioms and all others are checked similarly. So if we apply lambda.f to the element mu.x, then by definition, this is equal to lambda times f of mu times x. Using the linearity of f, we can move mu out, so this is equal to lambda mu times f of x. And since lambda mu is equal to mu lambda, product of real numbers is commutative, then using the axioms of the vector space, we can write this as mu times lambda times f of x. And if we apply the definition to the part of the expression which is in brackets here, we will get that this is equal to mu times lambda times f applied to x. And similarly, one can check all other axioms for the linear map and conclude that if we multiply a linear map with a scalar, we again get a linear map. And so on the set of linear maps, we have an addition and multiplication with scalars, and then it is very easy to check that the set of all linear maps with respect to this addition, multiplication with scalars, and the zero element being the zero linear map, this is a vector space. So we have a vector space of all linear maps. And we also have the coordinate map for this vector space. If we choose a basis in V, consisting of elements v1, vk, notation bold V, and let us choose a basis in W, consisting of w1, wm, and then a notation bold W. Then we have the map, which means we take the matrix of our linear map. So for each linear map F from V to W, we can take its matrix with respect to our basis V and W. So we start from a linear map and we get a matrix with m rows and k columns. So we'll get an m times k matrix with real coefficients. And the claim is that this map, which is in some sense an analog of the coordinate map, this map is linear and bijective. And the proof is exactly the same as the proof of this statement for the usual coordinate maps. And just a general reminder that a map is bijective if and only if it is invertible. Okay, let us finish with some problems and questions. Question 1. Check the axiom that the value of the composition of G and F at lambda.x is equal to lambda times the value of the composition of G and F at x for any two composable linear maps F and G. So check this with all details. Question 2. Check that if you have an invertible linear map F, then F inverse applied to y plus y prime is equal to F inverse of y plus F inverse of y prime. So check this with all details. Question 3. Check all the details in the proof of the claim that G is a linear map and the matrix of G is A in the invertibility theorem. So in the proof of the invertibility theorem, we constructed the inverse to F as some map G defined using its matrix. So check this part of the proof with all details. Question 4. Check with all details that the set of all linear maps with respect to our operations is a vector space. So a vector space has something like 9 axioms. Please check all these axioms. And question 5, check with all details that the map which assigns to a linear map its matrix, that this map is linear and bijective. Thank you very much for your attention and see you next time.